Hi, George. My name is Ryan Jordan, and this is my Physics 270 final. I thought I would do something a little different, show some variety. So instead of a skit or anything like that, I thought I would just do an explanatory PowerPoint for the 4 problems that I did. So I hope you enjoy. All right, so for chapter 11, I chose number 54, and the question is, why is the following situation impossible? A meteoroid strikes the Earth directly on the equator. At the time it lands, it's traveling exactly vertical and downward. Due to the impact, the time for the Earth to rotate once increases by 0.5 seconds. So the day is 0.5 seconds longer, undetectable to laypersons. After the impact, people on Earth ignore the extra half second each day and life goes on as normal, and we're to assume that the density of the Earth is uniform. So let's imagine what's happening. So here's the Earth and the equator. We have a meteor that strikes it and hits it. So first thing we're going to do is we're going to convert the 0.5 seconds into days, since we're really focusing on one full rotation, which is 24 hours. So we take the 0.5 seconds and divide it by 60 times 60 times 24 to convert it to hours, to convert it into days. So we find out that 0.5 seconds is 0.0000579 days. So next we are going to find the moment of inertia for the Earth. So the moment of inertia for a sphere, the equation for that is 2/5 times the mass times the radius squared. So we need to first find the mass of the Earth, which is 5.97 times 10 to the 24th kilograms, and then the radius of the Earth is 6.37 times 10 to the 6th meters. So when we plug that in, we get the moment of inertia for Earth is going to be 2/5 times 5.97 times 10 to the 24 kilograms times 6.37 times 10 to the 6th meters squared. And we find out that the inertia is 9.69 times 10 to the 37 kilograms meters squared. So we're gonna move all that stuff on. This is our important information, that the seconds to days and the moment of inertia for Earth. So in order to find the moment of inertia for the Earth after the meteor hits, we have to take the moment of inertia and then multiply that by the time change that the meteor caused. So it's gonna be 9.69 times 10 to the 37 kilograms times meters squared times 0.0000579 days. And we find that that is 5.61 times 10 to the 32 kilograms times meters squared. So now that we have this moment of inertia for the Earth after the meteor, we can go back and plug that into the equation to find the mass of the meteor, which is going to be the inertia equals mass times radius squared. So we have the inertia, which is 5.61 times 10 to the 32nd kilograms times meters squared, equals our mass times 6.37 times 10 to the 6 meters, and then square that. So we find that the mass of the meteor is 1.38 times 10 to the 19th kilograms. So why is this situation impossible? Well, after doing a little bit more digging, it turns out that Mount Everest weighs about 4.5 times 10 to the 14 kilograms. So the meteor being 1.38 times 10 to the 19th kilograms means that the meteor hitting Earth would be like 30,000 Mount Everest hitting the Earth at the exact same time. So the situation is impossible because humans would not be able to go about their everyday lives with a meteor that large. All right, so let's move on. So for chapter 12, I chose to do number 26. And this question says that a steel wire of diameter 1 millimeter can support a tension of 0.2 kilonewtons. A steel cable to support a tension of 20 kilonewtons should have diameter of what in order of magnitude? So we first look into the tension equation, which is going to be your mass stress times your area. So when we rearrange that, we find out that the mass stress equals tension divided by area. And the area of a circle, since it is a cable, is going to be 1/4 pi diameter squared. And since this cable is in proportion, we know that the max stress is going to be the tension over the diameter divided by, or which equals the same ratio of the other tension divided by the other area. So we know everything except for the diameter of the second cable. So when we put it together, we're going to get 0.2 divided by 1/4 pi 1 squared is going to be equal to the same thing as 20 divided by 1/4 pi diameter squared. And the diameter is what we are actually looking for. So when we multiply it by both sides, rearrange everything, we get this equation here. And then once we multiply everything out and divide and put everything off to the side, it turns out that we can get our d by itself. So d squared equals 20 divided by 0.2. So our d squared equals 100. So our diameter is 10 millimeters, and that is the answer we are looking for. So the diameter of the cable that can support 20 kilonewtons is going to be 10 millimeters in diameter. So for chapter 13, I chose number 49, and this question is saying that at the Earth's surface, a projectile is launched straight up at a speed of 10 kilometers per second. To what height will it rise, and we are to ignore the air resistance? So let's imagine it. We're going to take Earth, a projectile is launched straight up at 10 kilometers per second, and we are looking for the height. So we need some information. So 10 kilometers per second, we're going to convert that to meters per second, and we do that by multiplying that by 1,000 to get 10,000 meters per second. We also need the mass of the Earth, which we discussed earlier, and that's 5.97 times 10 to the 24 kilograms. We need the radius of the Earth, which is 6.37 times 10 to the 6 meters. And then we're also going to need the gravitational constant, which is going to be 6.67 times 10 to the negative 11th. So we're also going to use the law of conservation of energy, which states that the initial energy is going to be equal to the final energy. In this case, the energy that we are looking at is going to be, the energy that it starts is going to be the same as the energy that it finishes at. So the equation, since they're set equal to each other, is going to be 1/2 times the mass times the initial velocity squared minus the gravitational constant multiplied by the mass divided by the radius is going to equal our 1/2 mass times the velocity final squared minus the gravity times the mass divided by, now it's going to be our radius plus the height, since our final is going to be the full radius of the Earth plus that additional height that the projectile went. So we know that we can cancel the masses because they just cancel out once you divide over. And then we know that the final velocity is going to equal 0 because once it gets to the top, it's no longer going anywhere. So it's going to equal 0. So that whole equation on that side is going to be 0. So we know that it's 1/2 times the initial velocity squared minus the gravitational constant times the mass divided by the radius is going to equal 0 minus the gravitational constant times the mass divided by the radius plus the height. And we can rearrange everything and set it equal to 0. So we get 1/2 times the initial velocity squared minus the gravitational constant times the mass divided by the radius plus our gravitational constant times the mass divided by the radius plus the height equals to 0. So with that equation, we're still going to be looking for the height. So we have all those constants except for our height. So once we plug in all the information that we have, and we're going to continue plugging it in, and we're going to eventually be able to get the height, our h constant, to be by itself, and we find out that h equals 25,148,540.3, or 2.51 times 10 to the 7 meters. So that's the total height that our projectile traveled at that velocity for that amount of time. And finally, for chapter 14, I chose to do number 25, which states that a table tennis ball has a diameter of 3.8 centimeters and an average density of 0.084 grams per centimeters cubed. What is the force required to hold it completely submerged under the water? So let's imagine it. So with this ping pong ball, there are 3 different forces acting on this ping pong ball. We have the mass and the gravity pushing downwards. we have the buoyant force pushing upwards, and then we have this unknown force pushing it downwards to submerge it. So our mass times gravity, here's just the constants that were just spoken about. So since we are assuming that once the ball is submerged, it is not moving, we know that the mass times gravity plus the force pushing down, we can add that together and then subtract, that should be buoyant force, sorry. The buoyant force should equal 0 because the ball is not moving. And here's just some important information that was spoken in the question. The diameter is 3.8 centimeters times, that's the density that was given. So we also need to know the volume of the ping pong ball, which is going to be 4/3 pi r cubed. So once we plug in the radius, and we've converted this 3.8, cut it in half to get the radius, and then converted that into meters. So it would be 0.019 meters cubed for the volume, which is going to be 2.873 times 10 to the negative 5th meters cubed is the volume. We also need to know the pressure of the water, which is going to be 1,000 kilograms per meters cubed, and the pressure that the ball is exerting is 84 kilograms per meters cubed. So we just transfer over the important information that we just found on the first page, and we know that the equation we're looking for is mass times gravity plus force minus our buoyant force is going to equal 0. We can move everything around to get our force, which is the constant that we're looking for. So it's the buoyant force minus mass times gravity. And we know that that is the same as our pressure of the ball times the volume times gravity minus the pressure of the water times volume times gravity to equal the force. And then we just plug in all the constants that we already know to find out that the force is negative 0.258 newtons, which just means that the force that is being exerted on the ball to hold it underwater is going to be 0.258 newtons in the downward direction. That's what that negative sign means. So that is the end of the 4 questions that we were looking for. I hope that was helpful, and I hope I solved it. I know there was a couple hiccups in there, but I hope that was helpful, and I hope you have a great summer. Thank you so much.